So now that we've talked about assembly, which I think gives you an idea, well, the x86 assembly, which gives you or tells you how we're doing it nowadays, let's go ahead and jump back and at least study the single cycle architecture that we looked at before, and hopefully a lot more of this is going to make more sense to you now. Namely, if you recall from your assembly, and let's go and let me go look at it, let's see. It did start at the top and go one instruction at a time. Well, it actually started right here and went one instruction at a time, executing instruction one after another. So it is sequential, just like in C or C++. By the way, spoiler alert, C and C++ are just simplified assembly. That's all it is. So, and when I say simplified, I mean greatly simplified for your convenience. Try it again. All right, so let's go back here. It's executing an instruction one at a time. Well, how do we do that? We have something over here called the program counter. x86 called it the instruction pointer. Whatever, same thing. It is pointing, or it's keeping a counter to where the next instruction is. Well, where's the instruction? Remember, your program resides in memory, so you need to have some type of memory that holds the program, and that's what this instruction memory is. So your program is inside of this piece of memory, and the program counter is a register which holds what address your program needs, which holds the address pointing to the instruction you need to execute next. So you're going to execute instruction and then go to the next instruction. That's why this guy goes up here, we add one. We're just adding one to make all our lives easier. In x86, by the way, instructions can be length between 1 and 17 bytes, which means that this up here has to be way more complicated to figure out how many bytes the instruction is and go ahead and add it. But I'm going to simplify all of our lives and just say that every instruction is one word long. And so we're just going to add 1 to the program counter. The end. So the program counter is going to go 1 plus 1 plus 1 over again, and executing the instructions, or I'm sorry, incrementing the pointer to the next instruction every, I'll just say time for now, because we haven't talked about a clock. Program counter goes in instruction memory. We're reading the instruction. Well, the instruction memory outputs the instruction bits. What those are? If you recall from last time, there are different parts to it. Hey, look, the opcode. That tells you what type it is. Is it an add, a move, a compare, a jump address, etc., etc. Well, that's going to a decoder, very similar to our finite state machine, which activates one line in our control ROM, and that one line will dictate what all the control signals are to the different parts of our architecture. So what's going on the bottom is it's taking the opcode and then based on the opcode, telling each piece of the processor what it needs to do. All right, so that's the control ROM. What's everything else going on here? Well, remember in our instructions, just like in x86, you can have 2 registers. And by our convention, the 2 registers are going to be at these bits. In our convention, we also decided that we're going to have 32 registers, each of 64-bit width. Trust me, guys, it's just going to be simpler this way. I know that may be hard to see, but it's going to be easier. Goes into the register file, and it's going to go on these 2 ports. The register file is going to find that register in here and read the contents and put them on the orange line. All right, well, it puts it on the orange line. Hopefully the control ROM will select which one it is. For example, it was add to the contents of 2 registers. It would select this guy down here, forward it to the ALU, tell the ALU to do addition. The ALU would add it, and then send the result back to this MUX. Hopefully we'll say that since we're doing add, we want to select that data, put it in the register file, enable it to write, as well in this MUX, signify which operand we are writing to. So that's add. That's add. Does this make a little more sense now? So, oh, hey, look, let's do the add instruction. So we're going to add our destination source. Great. Destination equals destination plus source, PC equals PC plus 1. So PC equals PC plus 1. We're going to write that back. We send the two reads here. Both of them go to the ALU. Notice that this control ROM is activating the lines appropriately, which sends it back here, and we also are writing back to register 3 because that's the first one, and it writes it to the register file. Cool. I think this is where we stopped, wasn't it? I think so. Here's a question. How do we know when we're done? Hey, Sam. How do we know when we're done?
What?
How do we know when we're done?
When you get to that point.
Oh, I see your point.
In the code, do you put an end statement?
Well, I see what you're saying, but
Yeah.
remember we're executing one instruction. So an end statement would be another instruction.
At the end of an instruction, could you have like a trigger to tell you that it's done?
Well, I don't know what that would serve, because we need to know when is this instruction complete. When has in other words, for the add instruction, go ahead.
Don't you like set the amount of problems or iterations they have to do? So once the program counter does that many times, you're good.
Not when the program is done. When is this one add instruction? This add. When is the add complete? When, and I'm just asking when specifically, or as specific as you can tell me, does this one add instruction finish? When is add complete? When is add done? And we don't need to do anything or anything because add has completed. Well, how do we know when add's complete? Can we calculate it?
Yes.
Yes. All right, I know I was being a little, all right.
Yeah, you're good.
I know I'm trying to,
want
being a
to think?
little difficult here, but you got to really think about this because it's important. So, I mean, because does add, let's do it this way. Does add finish instantaneously?
No.
No, not at all. How long does add take? Well, you can just use the data structure answer.
It depends.
It depends, right, nice. Good.
We've learned 2 words.
Great. What does it depend on?
Your architecture.
You're well played, ma'am. You are correct. More specifically, what about in this architecture that I have presented, how long would it take? You can also say it depends as well, because that does actually answer the question. True. And what in this architecture does it depend on?
Your gates.
Your gates. Perfect. Beautiful. So remember how we were sitting there and trying to do gate delays that entire time? Now you're going to see why. Well, well, how many gate delays are those muxes? Ooh. Well, it's a 2 by 1 1-bit mux is that, but we have a 2 by 1 32-bit mux, actually, hold on. What do we have? This one is 32, I'm sorry, this is a 2 by 1 6-bit mux. This is a 2 by 1 64-bit mux. Oh my goodness. Let's think about this for a moment. Well, they're still 2 by 1. So you're still going to have we're going to go with the 6, so I don't have to draw 128 lines. I only have to draw 12, which I think I'm already out. 4, 5, 6, 7, 8, 9, 10, 11, 12. And we just went 1, 2, 3, 4, 5, 6. Hey, look, we have one selector bit. And sure, we'll do A0, B0, A1, B1. Let me actually do it the way you're going to do it in Verilog. That way it makes more sense to me, but we're going to do it in how you would in Verilog, which would be A0, A1, A2, A3, A4, A5, B0, B1, B2, B3, haha, B4, and B5. Okay. And then, of course, you have out, out not, huh, great. Out 1, out 2, out 3, out 4, and out 5. Okay. Well, let's start with our simple one. Now I will go to this mode. A, B, O, S. What's the gate delay of this?
About 10.
5? I can't remember. I forgot.
It's 4 or 5, I believe.
I mean, I'm just going off the one I did. It was about 10.
Yours was 10? No, we'll say 5. How long is that going to be?
At least 5.
6 times.
At least.
Or no less than 5 is going to be a more accurate statement. Okay. Well, how could we do this? Well, let's think of out 0. What's out 0 going to be? Well, hold on. It's going to be A0 if S is 0. It's going to be B0 if S is 1. Right? Wait, what does that sound like? Yeah. Nice. Okay.
So this would just be 6 muxes in parallel, right?
Huh. You got that? Because what would O1 be?
Will be different.
A1 and B1, those are your two options. S comes in, O1.
Yeah.
Is O1 dependent on O0 at all?
Nope.
No. So how many, so what do you really just have? You have 6 2x1 muxes in
Yeah.
parallel. So what's the gate delay of this? It's the same as that. Because you're taking advantage of parallelism. Now, for this course, we are going to just assume that they're the same. In real life, there's going to be what's called a fan-out cost, because you'd have to fan the S out to each individual mux, and that will probably add a gate or two of delay, but we are going to ignore that for the purposes of this course. So for the purposes of this course, the 6-bit one is the same as the 1-bit one, and what about the 64-bit version? It's the same as well. Now, is it a bigger structure?
Yep.
Yes, but the performance is the same. It just consumes more area, more power. Again, you got to really think about the fact that everything's happening in parallel. All right, so that's 5. What's the register file? Well, we haven't talked about that, so let's just call it 20. Ooh, here's another mux. You don't even have to tell, and it has 2 inputs and 1 output, so we don't even have to think about what its bitness is. It's 5. ALU. Ooh. Well, how long does it take to do an addition? That is a tough question. By the way, people have been paid millions of dollars to figure out faster ways to do addition. And I think it's the Pentium 4, I believe, still has the current version of addition, which is a very interesting quantum mechanics result of how addition works out. We're not going to be doing that in this course, but addition is something that the ALU can be vary a lot. But we'll say for the sake of argument it takes 100 cycles, or 100 gate delays, which is actually pretty reasonable. All right, and then it's got to go back to that other mux, so that's another 5, and then go to the register file. Let me see if I have a picture of that. Sure don't. Okay. So we're going to skip ahead, because I know I do. Boom. We'll say the instruction memory is 20 gates deep. Looks like these muxes were 8. Then we got to add the ALU. And yeah, how much? Well, we'll just say it's another 100 and then goes back. Okay. So then how long does the add instruction take? There, we'll say that. How long does the add instruction take? 140, 150 roughly, because it's got to look at the critical path. It takes 20, actually 28 to get to here, plus another 5. Wow, that totally got ignored. Oh wait, no it doesn't, because to read these operands doesn't require this mux, the input of that mux. So these 25 and here, looks like you just added another 2 for some reason, that's fine. ALU added 90 something, came back here, had to go to that mux, added a couple more. Looks like this might be a little off, but that's okay. All right, so that means we need to wait about 150 gate delays before we fetch the next instruction, right? Okay, how do we do that? We have a clock. So this makes it a sequential circuit to predictably change state or store information. The clock says it's basically the gatekeeper of this instruction is executing, it's done, let's go to the next one. It alternates between 0 and 1 at a fixed frequency. Our modern processors can actually change the frequency on the fly, but we're just going to assume for the sake of this course that it is always fixed, aka 100 megahertz. What should the clock frequency be? Do we want it to be as high as possible or as low as possible?
High.
It's just not your day, Perry.
I know, it's 50-50.
Why do we want it to be as high as possible, guys?
You get more
More done.
done.
Now, a couple things I want to point out. The higher your clock is, the more energy you will consume. Just keep that in mind. But in general, for performance reasons, we want the clock to be reasonably high, where we have acceptable power draw and our processor doesn't melt. By the way, at 1 megahertz, you don't need anything. It just runs and you're good to go. But once we got to about 100 megahertz, you need to put a heat sink on it, otherwise it would melt. And then I'd say probably around 400, you had to put a fan on that thing, as well as a heat sink. And then I'm sure if you look at hardware nowadays, there's plenty of different heat sinks that have gotten very big, as well as liquid cooling is now available as well, because it just gets that hot. But just wanted to keep you in mind of the issues with the frequency. So a clock, periodic pulse generating using oscillating crystal, distributed throughout the chip using clock distribution. By the way, it is actually somewhat of a difficult problem to make this clock as consistent as possible, especially when you're operating at 1 billion cycles per second. So there are research institutes that just are trying to make the clock as accurate as possible while making it as cheap as possible as well. We've gotten pretty good at it. But just so you know, this is not like something you get for free. It took us a while to get here. But with this clock, we can create a new class of circuits that are called sequential, which means that the outputs are determined by the inputs and the previous state that we were in. This is important because that means we can execute an instruction, save the state, and when we go to the next instruction, we are basing it on our inputs and what the previous state was from our previous instruction, which is what we want when we're coding, because we execute one at a time, and when you're at the second line, you assume that the first line completed. That's what we want, and that's what this clock will give us. All right, we talked about an edge-triggered flip-flop. So the idea on this version, let's see, you have data, it's high right now. Where's the clock? So clock goes up. When the clock goes down, it is sealing the data into the master latch, because then once the clock goes to the bottom, the the gate control here is 0, which means it's not going to overwrite over the master latch. When it comes back up, notice that the SR latch, let's see, when it's down, that means that this guy is going to change to what this latch was. And so it'll actually push the final data, let's see, Q out as well. When the clock goes back up, notice that this guy is going to be knotted on control, so he's going to hold that previous value while the master latch receives the new value to seal. And then when the clock goes back down, that data value is sealed in this latch and is written into the slave latch, which holds it until the clock goes back up, which outputs here, and then the data value can receive a new one to seal next. So it's flip-flopping in that there's this idea of sealing the data, outputting it until it moves on. This is very, very important because you want your registers to be outputting the same values until you're ready to seal in the next value. And that's what the clock gives you. And you can have the other edge triggered as well, is what this is saying. So was it edge trigger? What's the top one's like a toll gate, the other one's like an airlock. So the toll gate is you have to pay before you can get on. The airlock is you get in, stuff happens, and then you're allowed to get out. The nice thing about flip-flops is we can think of them as instantaneous change of state. I put in quotes instantaneous because that does not exist, at least in circuits. Let's put it that way. But we can just assume it does for all of our engineering purposes. Okay, so hopefully this AND will make more sense. We have an AND instruction. We're going to have other instructions. Do you think other instructions may take the same, less, or more than the AND? Come on, guys, data structures. It depends, right?
That's the answer to everything.
My classes. Shifting is faster than addition, so a shift would take less time. Multiplication is really a bunch of additions, so it's going to take a lot longer. How do you determine what your clock frequency is?
Can you set it?
Set the clock frequency?
Yeah.
Yeah. For our purposes, let's say the clock frequency is set during manufacturing time. So once it's set, that's what the clock is. And so when we're going to produce our chips, we need to set or lock in the frequency. How do we determine what that frequency is locked into?
Whatever operations you want your computer to be doing most of the time.
Most of the time? Or you want all your operations to execute, correct? So which operation will dictate how long a clock cycle is? The longest running one, or your slowest operation. So that's a very important takeaway as well. All right, let's go ahead and stop for now. I kind of wonder if there's